Okay, so welcome everyone. We've met this afternoon to look at a masterclass in using tools for big data, which is a very broad topic, but I'll narrow down and drill down into that as we go along. And we've got a broad audience of maths, computer scientists, economics backgrounds, and so we'll try to do something of interest to everyone as we go along. By way of background, I'm currently a Turing faculty fellow, one-day-a-week faculty fellow. The rest of the time I'm based in the computer laboratory at the University of Cambridge, where my focus of research is into networks, in particular flows in networks, congested networks, looking at applications in communications and in other things like transport and energy networks. So my big picture summary for this afternoon is there are three topics that I'd like to convey in some degree or other. These three topics are to discuss statistical learning, but in particular to discuss it with, complement that with the discussion about how R, the package R, can be used to good effect in that area. The second one is specifically to look at the role of what's called tidy data and this so-called data wrangling. So how can we use tools to help us keep our data tidy, and why should we do that anyway? And also how should we manipulate the data to bring it to life, to make it useful in various sorts of visualizations and various sorts of modeling contexts. And then the third aim, so these are fairly practical aims, the third aim is to introduce you, if you haven't seen it before, to the RStudio software environment, which is, I think, a very nice environment now to use R. And I'll give some examples of that. In particular, I want to give examples where we use documents like R notebooks, which are sort of contain executable chunks of R code, together with the outputs, like the numerical outputs, but also the graphical outputs, which are all stored together in a single file. I think that's a very nice way to package our work together. I understand that in earlier masterclasses that you may have attended, you've looked quite specifically at statistical learning, statistical methodologies, and also you've been having classes in the area of software tools, for example, an introduction to R. So I'll assume a little bit of prior knowledge there, but as I say, what I want to do is to really bring them together in a fairly practical discussion about how statistical learning can be discussed, and using R to bring that to life. I think what I'll do is I have slides prepared on all of these topics, but the bulk of the slides are in the first topic on the statistical learning. I think maybe we'll sort of cut between these two or three different topics as we go. So I won't just go through the statistical learning as a big bulk of slides and then move on to the practical things towards the end. I think I'll bring some of that forward, since I think there's probably considerable interest in that this afternoon. In the area of the statistical learning, I'm going to present some work that is from this wonderful book by James, Witten, Hastie and Gisbert on statistical learning with applications in R. I wonder if people are familiar with the book already? A few of you, yes, okay. So I think it's a terrific book in many respects. It's a modern book, it's an authoritative book, and it's a very engaging book. It's very easy to read and get the real insights about what's going on in these statistical modelling ideas. What I'll do is present some of the things which you can read more about in this book. In fact, you don't even have to buy the book, because the book is online as a complete PDF at the author's websites listed there. Another nice thing about the book is that the chapters guide you through a discussion of statistical learning from the introduction through to looking at regression style problems, where we try to fit models appropriately to data, where the response variable is a quantitative variable, so a continuous variable, and each of the chapters has at the end what they call R labs, which is a very nice walkthrough for somebody who doesn't have to know a lot of R, but it uses the R facilities which complement the material in the chapter. So there's a nice R lab on regression type models, similarly on classification type models, and so on. So a very good place to go for information about using R is the end of each of the chapters in this book. It's fairly, how can I say, it's a slow-paced R. It's not very sophisticated R that they present there because they want a very general audience. And I think the facilities in R now can be used to build quite efficient and quite nice environments, sort of pipeline environments for doing the statistical modelling. I think we'll discuss some of that this afternoon, although there isn't much of that type of the story in the very nice book. Okay, so what I'll do is I'll look first at these ideas of statistical learning, and I'll sprinkle in some examples of R, and I'll discuss as we go along those features of R. And then in due course we'll move on to look at the more sort of practical side of data, tidy data, data wrangling, and also the use of RStudio. How many people have used RStudio? Oh, okay, so I'm sure there are people here who are far more expert than I am, so do add suggestions as we go along, and indeed at any time add suggestions as you go along if you want to raise any issues. Okay, so let's delve into the statistical learning then. So the context for this, introduction for this, is that we suppose that we observe a number of variables, and these variables are potentially able to predict a response variable y. There may be a set of variables, p predictor variables, let's call them x1 up to xp, and in some way there may be some association between the values of the predictor variables and the response variable y. So the sort of working hypothesis is that these predictors, or at least some of them, not necessarily all of them, some of them may be valuable in building a model through the representation f, which takes you from the predictors through to the response variable y. But it's not going to be a complete exact model. There's always some error associated with that, and the error term will be given by the expression epsilon. And we'll assume minimally about epsilon at the moment, we'll assume that the errors are independent across the different observations and that there should be a zero mean for that error term. If you didn't have a zero mean, then I think you'd sweep it into the function f. Okay, so along with the book, the statistical learning book, there is a package you can download for R, which gives you access to some functions and some data sets. So as we go along, I'll refer to some data sets which are ones that are made available in the package. The package is called ISLR, so Introduction to Statistical Learning with Applications in R. And the first one, once we've loaded that package, so here I'm showing R code, the commands with the prompts followed by the output. So the library command makes available the package ISLR into your working session. So previously, if you haven't already got that package, you have to download the package from the CRAN, CRAN archive of packages, of which there are many thousands of packages now. But once you've initiated that library in your session, then it makes available to you a set of additional R objects, which can be functions or they can be data. For example, the wage R object, if we look at the names associated with that object, then they're listed here with the names command. And so the wage object has a number of variables associated with it, which are linked in with this idea of a wage. So here what we're doing is looking at the head of that data frame, that R data frame, which is to say the first 6 or so lines of that data frame. And the indexing into the data frame is through the square brackets arguments, the first of which is blank, which means all the rows are available, and the second of which is nominating the columns. So this is the conventional way in which R allows you to subset into a sort of a matrix of the information given by the rows and the columns. So here we're asking for the columns labelled year, age, education and wage, and the first 6 or so of those are printed for us here. So that contains some numerical data and some text data associated with this education value there. Throughout these slides, I'm using an R package called knitr, K-N-I-T-R, which is a package to do what you might call literate programming or reproducible research. What you're doing is you have a document which is simultaneously in part R code and simultaneously in part, in my case, LaTeX. And so I can build slides using the LaTeX, which has arbitrary maths and all the other capabilities of LaTeX. But embedded in there was some R code, which is executed, and the output is made available back into the LaTeX. And that's both text output from the command prompt, but also, as we'll see, you can include the figures as well. That's a wonderful thing to be able to automatically include the figures in the documents, rather than saving them with a funny file name you have to think about and then remembering the file name when you insert it back into LaTeX. So all of that's kind of going away now, and people use these types of facilities. knitr is the one that I think works very nicely with LaTeX, and I use it a lot for my slides. We'll see later that RStudio gives you an even simpler way of doing all that in the context of the RStudio package. Okay, so there we are, we're just looking at some data. Now let's have a sort of visualization of some of that data. So this is a graph of the wage values against the age values. So these are wages of individuals with given ages, given education levels, and so on. And the way I've produced that graph is using the command at the top there, which is a set of commands in R, which use a package called ggplot2. And I'd quite like to illustrate many of the things we do using this ggplot2 package, because I think it has a very nice, offers a very nice range of building facilities for building really quite good quality statistical graphics. However, as with lots of things in R, there is quite a steep learning curve, so I hope that these sort of snippets of R code and then the graph will be useful to you and sort of inspire you to use it as well. So the way in which this works is that, I'll try using this after all, is that the ggplot command here is first, it's given the data frame of data to work with. That's the wage data frame. And then I've given another argument to this overall ggplot command, which is associating what they call in ggplot language the aesthetics. So the aesthetics of the plot are things to do, for example, with the x-axis is one aesthetic associated with the data, similarly for the y-axis. So AES is their abbreviation for an aesthetic, a visual aesthetic, and what we're doing is linking the x-aesthetic, the horizontal variable, with the age variable in the data frame, and similarly the y variable is associated with the wage variable. That is enough data to sort of draw the coordinate system, but then we put, in addition to that, we embellish the plot with various information. So you're able to, with plus, add to the existing ggplot with something which is geometric related, and the idea is that you're going to put points at each of the xy positions, which is shown here. And as with these plots, if you do many points on the same plot, you soon realise that you want to have control over the size of the dots, because they overlap a lot in this case. So there's a size parameter, which is a sort of generic parameter in many of these graphical commands, which controls the overall size of what's being plotted. So size equals 1 produces dots of about this size. You can obviously make them much smaller, or you can make them much larger. Here I've added in a few other facilities to augment this plot. So here I'm controlling the way the y-axis is described. So the y-axis here, I'm forcing the limits to be 0 at the bottom and 350 at the top. Otherwise it would choose its own limits. It usually has good defaults, but if you want to override them, you can do it that way. And in addition to the points, I've used the statistical smoother, to add in the blue line here. So this uses some sort of smoothing technique. Obviously the details you can discuss in the documentation for the ggplot2. It's a local regression type smoother. You can control the level of smoothing if you don't like the default level. You can change the colour of the line that's added. Here I've said standard errors false. Otherwise it would produce a ribbon associated with the standard error to estimate this blue line, which I've removed by saying SE equals force. Okay. So emphasising visualisation early on, because I think visualisation is a really important aspect of the way in which we engage with data, especially large data. The other one is models, and I think visualisation and models sort of go hand in hand. So I'm emphasising ways in which to do the visualisation. Later we'll talk about the models. Okay, so I won't dwell on this one, except to say now that we're using year instead of age. So we have wage data every year shown here, and a smoother which is given by linear regression, so the LM model, linear model. There's a slight upward trend, inflation in wages. And lastly, if we look at wages and then separate out according to the educational level of the individual, then what's shown here is a box plot. So the box plot is obtained instead of G on point, which would just produce the individual points. It instead produces a box plot where the fill type, so the colour, is given by the variable education. So every individual had an education level, and there was 5 of those shown here. Guides is the term they use for the sort of legends that you might want to put on the side of these plots. So I've said the guide associated with the fill aesthetic, that's to say the colour associated with the educational level, I said that's false, which means no such legend should be produced, which I think is redundant in this case since it's clear the association between colour and educational level. And you get better use of the space. Okay, so arguably more education leads to higher wages. Okay. But there are of course outliers in each of these cases here. Are box plots familiar to everyone? So box plots is a way of indicating some information about the variability in the distribution of wages for each level of this educational parameter. The box itself is the interquartile range, so 25 to 75% of the data. These so-called whiskers are lines extending beyond the interquartile range out to any data point that is, or rather the furthest data point that is no more than 1.5 times the interquartile range. And then any data points that are beyond that whisker level are shown as individual dots. At that point there ought to be rather few of them. Okay, so what remarks can we deduce from looking at those plots first of all? So, provide evidence that wages increase with age, but then there was some tailing off after about age of 60 as people sort of withdraw from the labour market. Higher degree of variability about that trend, but it's unlikely that purely age alone would lead to accurate predictions of wages, since we've seen educational level is such a strong factor as well. There was some inflation in ages. Wages roughly increased by about $10,000 between 2003 and 2009. Wages typically increase with the educational level, and we might expect that most accurate wage predictions would arise by taking into account of all 3 of those predictors. Okay, so quickly look at a second example. In the second example, which is from some data which is made available with the Statistical Learning book, you can download from the same website where the book is made available. So there's a CSV file which you can read into R using the read.csv file, CSV function. Let's call that a data frame, and then the top 6 lines of that data frame are shown here. So this is a data frame with sales in some units together with expenditure on various types of advertising budgets. So there's a budget for TV advertising, another one for radio advertising, and a third one for newspaper advertising. Similar R commands to plot the sales against the TV advertising budgets. We see that the more spent on TV advertising, the higher the sales. Likewise for radio, although there's quite a big spread of the data points and possibly non-linear spread as well. And similarly for newspaper. Okay. So questions you might be interested in asking with this kind of attempt to find the association between the predictor variables and the response variable would be how would we increase the sales by affecting expenditure in the advertising budget? Which of those advertising budgets should we increase and which should we decrease? Bits of terminology here. So the independent variables are sometimes known as the input variables or features, and the output variable is sometimes referred to as the response or the dependent variable. That's to say dependent in some way through an association on the predictor variables. Okay, so going back, we want to somehow find this function f, which allows us, if possible, to find that association between the features x and the response variable y. And I think they're worthwhile just picking off two different aspects of why we might want to do that. One is prediction, given input variables, given features. How would we predict that response variable y? How would we predict the level of sales given our choices over the advertising budget? But secondly, rather than that prediction problem, there's also an inference question, which is how do I understand the relationship between this predictor and the response variable? What is the, as it were, the coefficient per unit increase in advertising budget on TV? What does that turn into sales? So I want to sort of see inside the box, see inside the model to work out how individual variables are associated with the response variable. And that may be just as important as simply producing accurate predictions. Okay. Now, in making those predictions, we need to somehow estimate the function f. So the statistical terminology for this is to put hats on the quantities. So after you've estimated the f from data, let's call that f hat. And then the prediction, the y hat, is f hat of x. Okay, the errors with us, the residual random errors, we can't predict those. What we do is we predict with mean 0 for the errors. So in doing so, we should be aware that there are really two types of error when we make that prediction. The so-called reproducible error, which is due to our imperfection in estimating f hat. So maybe we didn't have a very good technique for finding f. Maybe we had just had too little data to build a very good quality predictor f. But that is potentially a level of error that we can try to reduce either through better modelling or more data. But secondly, there's the irreducible error, which is the error associated with the epsilon term. And that's one that's sort of out of our control. Okay? We have to sort of live with that. Okay. Okay. So I think I'll probably skip this one. It just says that the mean squared error is the sum of those two errors. Okay. In a practical context, we may not just want to sort of know a black box, know the f hat. What we might want to do is answer questions about which of those predictors are involved in the f hat. They may be costly, expensive, arduous, painful to determine the x variables. We don't want to measure them unnecessarily, so we want to be selective about those. So we want to know which ones are really associated with response. And also, what is that relationship between the response variable and the predictor variables? Is it a nice, convenient linear type relationship, or should we move on to a sort of more complicated non-linear type relationship? Okay. And very often the simple linear models allow us to make quite straightforward and robust models, but sometimes they're not sufficient and a sort of non-linear type model is appropriate. But I think often we'll want to start with the linear type model and work out from there and extend that. Okay, so I think maybe what I could do is just very quickly just walk through the idea of estimating parameters in a model fitting context. I'm conscious that we probably have seen much of this before, so I won't dwell on this too much, but just for notation at least, let's suppose that we're given a training set, which is a set of observations both of the predictors, x, and of a response variable, y. And we're given that for each of n individuals or n observation units. So the x's themselves can be multivariate. Maybe there's p components to that x. And our goal is to estimate an unknown function f using the training data. It's training data in the sense that the response variables y are available to us and allow us to train, to sort of hone in or guide us to select our function f. So we've got information both on the predictors and on the response variable y. And I'm going to concentrate on parametric models for f. There are also non-parametric ones as well, which I'll talk about. Okay, so the sort of classic way you might set this up would be a linear model for the function f, governed by various parameters beta naught up to beta p. One here, the first one here would be an intercept parameter, and then this would beta 1 up to beta p would sort of gauge the strength by which we take the predictor variables and influence the response variable. And the usual way of starting to set up a model to find, set up a procedure to find those betas is through ordinary least squares. That's not the only way by any means, and the book I keep referring to, The Introduction to Statistical Learning, starts with this, and then in later chapters moves on to really quite nice ways of, instead of ordinary least squares, we might have a formulation which is a constrained optimization problem rather than an unconstrained optimization problem as you have with ordinary least squares, trying to minimize the mean squared error. But you could put in constraints associated with the size of the coefficients, the size of the betas. These are known as usually shrinkage type methods. So why would you might do that? Well, you might do that because you want to penalize the presence of predictor variables in your model, because you prefer models, let's say, with fewer predictors. So if you can squeeze out predictor variables which are not adding a lot of value in predicting the response, that's to say, give them a cost, and if in that constrained optimization setting you can yield models with far fewer parameters often, which makes them more readily interpretable, but also maybe much easier to operate and cheaper to run because you've got fewer predictors to measure. So there's a very nice chapter in the book on shrinkage methods which go beyond ordinary least squares, and there are many R functions which enable you to do that. So essentially what's happened then is that we've reduced the problem of finding the function f to simply finding a set of beta naught up to beta p, so p plus 1 parameters. Okay. And there's a very nice remark here in the book about the role of simple linear regression. It's obviously a very simple technique, makes strong assumptions about the linearity of the relationship between the predictors and the response, but it's often the starting point for more elaborate and more flexible models. And a comment in the book, the Introduction to Statistical Learning book, is that consequently the importance of a good understanding of that linear regression, a good set of tools to work with it, before studying more complex learning methods cannot be overstated. They say that very emphatically in the book, so I'll say it at least once. Okay, so here are some similar questions about the advertising data set. Suppose we had that model, what would we want to do with it? Well, some of these questions are inference questions, some of them are prediction questions. So is there a relationship between advertising budgets and sales? Well, we've seen examples of graphs which strongly suggest that there is. If so, how strong is that relationship? And which of the different advertising media contribute most to the sales? So that would be a question about how would we estimate the betas and how big are those betas? How accurate is the overall estimation? Estimating the parameters, so the betas, but similarly, how accurate are we at predicting the future sales? And at the end of the day, are we content with this linear relationship, or could we move on to a more elaborate model with non-linear relationships between the predictors and the response variable. And maybe we might have a more complicated structure to the model where there is some sort of synergy associated with advertising, which means that it's not individual terms x1, x2, maybe it's the product x1, x2 that we should bring into the model. Okay, so what I'll do is just very quickly indicate how we find these beta parameters. So what we're trying to do is, let's say, have a model with TV advertising associated with the response variable, the sales, and we want to find the beta naught and the beta 1, let's call them beta naught hat, beta 1 hat, using a least squares type technique. So, well, first of all, there is the data, and these are the little, what you might call residuals, which are the difference between this particular straight line and the data points, the red data points. And what we're going to try and do is to find the betas which minimize this residual sum of squares, which is the sum of the squared discrepancies between the true values yi and the fitted values yi hat. Remember, this is a context where we have a training data set, so for these observations we do indeed have the yi's, and this is where they're being used to train, to influence the choice of the betas. So this is the residual sum of squares, which we also write like this. So this is just the maths behind finding betas which minimize this quantity. So that's a convex differentiable function, so we can find those betas by looking at the stationary points of that function. So we take the derivatives both with respect to beta naught and then beta 1, and doing the little calculations which we won't go through now. Then beta naught hat is the average of the y minus beta 1 hat, the average of the x, from that analysis of the stationary point with respect to beta naught. And similarly with respect to beta 1, we get this term at the end here as the fitted value for beta 1. So sort of convex optimization, differentiable functions, we can find these betas readily. And what is it doing? Well, if this is the contours of this function here, which is the residual sum of squares for parameter beta naught and beta 1, then what you're doing is finding this red dot here at the minimum of this convex function. This is the sort of picture associated with this very simple linear regression model, but many more elaborate models will have similarly surfaces which are minimized. There may be more elaborate techniques required to do that minimization, but it's essentially this story. Okay. So how would we do this in R? So how would we get our hands, given data, how would we get our hands on the beta 1 and the beta naught? Well, the way it's done in R is that you, let's say, reading the data through read.csv. If you pass that data argument to the LM function, which will fit a linear model for you, then within that data frame there were variables sales and TV, and this is a so-called model formula which relates the left-hand side, the response variable, to the formula on the right-hand side, which in this case is just a single variable TV, but you can build more complicated formulas involving multiple variables as well. So the return from that, let's say lm.out, is an R object that has many components to it, but embedded in those components are the information about the coefficients, the betas, for example. So one can obtain that, for example, through this function coef to obtain coefficients out of the return value lm.out, and it will list for you the beta naught and the beta 1. So what it labels the intercept would be our beta naught, which is around 7, and similarly the beta 1 is around 0.047. So to make that interpretable, that is saying the model is fitting parameters beta which say that the sales increase by around 47.5 units for every $1,000 spent on TV advertising. In the model formula here, I just gave the predictor variables because R will implicitly add a intercept variable, that's a beta naught variable. If you don't want it, if you really do want to fit a model where the intercept is 0, then you can force that by putting in the model formula on the right-hand side a -1, 1 is the sort of indicator for the intercept term, so -1 means withdraw the intercept. Okay, so let's think of how we might discuss the betas. So the betas have been obtained by estimation using data. Let's suppose that there's a true model given by beta 0 and beta 1. Of course, we don't know those parameters. All we know is data, and then we infer from the data. And let's suppose the model was beta 0 is 2, beta 1 is 3. And suppose that these epsilons, these error terms, are zero mean, they're independent over observations. But let's suppose, just for the purpose of producing a synthetic data set, that they have a distribution which is normally distributed with some constant variance and mean 0. Then in the next diagram here, what's shown is, what's shown in red is the population regression line, that's to say with parameters 2 and 3. And what's shown in blue is what arrives after doing the R-fitting. You obtain some beta 0 and beta 1, which are not exactly 2 and not exactly 3. They're just slightly perturbed from that. If you did this many times, you'd get different blue lines. And on the right-hand side is shown that variability of lines, that's to say variability of betas, as you did fitting with more and more examples of the training set, specified in the same way, but it's indicating that the population line is something that we never see. All we see is these inferred or estimated lines, which average out, I'd say, roughly to that red line, but of course there is some error associated with it. Okay. And the way in which in statistics we discuss the standard errors, I'd like to sort of mention this example here because I'll come back to it later and show some, I think, more interesting statistical procedures which make more robust procedures around the bootstrap idea, which I'll discuss in relation to this. So here we might, under assumptions of constant variance for the residuals, for the epsilons, then you can estimate the standard error, in fact the standard error squared I should say, of the beta 0 parameter and similarly the beta 1 parameter. They turn out to be given by these formulas here, which a statistics textbook would tell us how to obtain those formulas. But if we look at those formulas, they do sort of make some sense, do they not? Because let's take the second one. So it's saying the standard deviation, the standard deviation squared, so the variance of the beta 1 parameters averaged over many fitting instances is given by this formula sigma squared, where sigma is the constant variance for the errors, divided by this quantity. So if all the x's are very close together, that's to say they're close to their mean, then this is going to be quite large. Whereas if the x's are well spread out, then this will be much smaller. So that's just telling us, I think, what is quite natural. If all the data points are very close together, then our estimate of the slope is going to be much harder, going to be much higher estimate, higher variance for that estimate. We go back to the data here. If all of these x's are very bunched together around their mean value, then it's going to be hard to estimate a slope. Okay. Whereas if they're more spread out, then it's lower variance. So that makes good sense. And also, if the mean of the x's is in fact 0, then the standard error of the beta 0, that's to say the intercept, will be just the standard error of mu hat, the average of the data. So again, I think that is readily available. Okay. This standard error, the sigma squared, might itself be estimated through the residual sum of squares. So there are essentially n-2 degrees of freedom left because we've estimated two parameters, the beta 0 and the beta 1. So we scale by that n-2, and then the square root of that is so-called residual standard error. Okay. Other things we can do with these standard errors, well, we could extract at least approximately a confidence interval for our parameter beta 0, and at least approximately, if we add plus or minus 2 standard errors to these parameters, then we'll have confidence intervals where we are 95% confident that the true parameter value lies within that interval. So the interval is constructed from data, and then we fit the betas to get the beta hat and the standard error. And then this region around that value, the beta naught hat, gives us the width of that gives us control over how much confidence we have about beta naught exactly lying in that interval. And if you take, very roughly, if you assume normal errors, then very roughly 2 standard errors gives you a 95% confidence interval. Okay. The betas and the standard errors are used in hypothesis testing in the following way. So we might have, having fitted a model, how do we judge whether there is some appropriate association between the predictor and the response variable? Well, we could set up this kind of hypothesis as follows. So let's suppose the null hypothesis is that our slope beta 1 is 0. So there would be effectively no association between the predictor x1 and the response variable y. Alternatively, the beta 1 is non-zero. So we're interested in whether the beta 1 hat is sufficiently far away from 0 for us to then reject the null hypothesis and perhaps accept this alternative. Okay? But the question is, how far should beta 1 hat be away from 0? So presumably that is controlled by how variable beta 1 hat is. If it's got high variability and we observe a reasonably high value of beta 1 hat, then that could just be due to the chance variability of beta 1 hat. Okay. So that leads to this idea of so-called t-statistic. So if we look at the quantity beta 1 hat minus what it would be under the null, that's 0, divided by the standard error. So how many standard errors worth of deviation are we away from 0? Well, this quantity, if beta 1 is equal to 0, can be shown to have a t-distribution with n minus 2 degrees of freedom, which is actually very close to a normal distribution, so for large enough values of n. So what we would do is, under this assumption that beta 1 hat is 0, let's say the null hypothesis, we would, under this assumption, this result here about the t-distribution, we'd ask what's the probability of observing values which are greater than the t statistic given here, beta 1 in terms of units of standard error, and that's the so-called p-value. So if that p-value is small, then what we're doing is seeing something that's rather unlikely to have occurred if the null hypothesis is true. If it's sufficiently small that we would then say less than 5% or less than 1%, then we would say that we would reject the null hypothesis that beta 1 is 0 for the alternative, namely that it's non-zero. Okay. So these p-values are the way in which we can decide whether the predictor variables are valuable in the model or not, or whether they just not related to the response variable. Okay, and in practice with R, suppose we were doing this TV model, so we fit the model here as before, we obtain the coefficients, but here if we use the summary function and then the dollar command enables us to extract the coefficients part of the summary function. What it does is not just the estimates, which we've seen before, but it calculates these standard errors and the t-values and the p-values. So with these p-values being very small, say for this one, the beta 1 here, it's 10 to the minus 42, it's very small, it's saying that it would be very unlikely to have observed a beta so large in terms of units of standard errors that it would be implausible to suppose that beta 1 was itself 0. Okay, I think we'll just wrap up here just by looking at this R-squared measure. So the R-squared measure gives us an overall sort of goodness of fit measure. So we take the total sum of squares of the variability in the response variables, that's yi minus y bar, the average y, square those and add that up over the observations 1 to n. That's the total variability in the response variables. We've currently got residual sum of squares, that's to say the yi's minus their predicted values of this amount here. So this ratio here is describing the amount of explained variation under the model. So if that R squared is close to 1, then the model has explained a large proportion of the total sum of squares, the total variability associated with the y's. So that would be a very satisfactory outcome. However, if it's close to 0, then either we've got a very poor model, we haven't succeeded in explaining a large proportion of the variation in the data, or the sigma squared is high. So the sigma squared is what controls the level of residual sum of squares. So either of those could be true, or both. Okay, so it's a bit more subtle to decide what to do if the r squared is close to 0. It's easy to settle on what happens with r squared close to 1. Okay. All of this can be extended and done very straightforwardly in the R system to a multiple linear regression where we've got multiple predictor variables here, and the sum of squares, residual sum of squares, will be given by these quantities here. Okay, so I think we should stop at this point and pause for a moment. Maybe there might be some questions on this material. Okay, I think what we should do is I should just sort of switch modes a bit to look at the more practical aspects with the R. And the way I'll do that, I think, is to jump forward in these slides to a later part, and I'll talk through some of the use of RStudio, and then we'll look at some particular aspects of data wrangling, building on that. So let me first of all switch to just briefly discussing about RStudio. So I'll do that by jumping forward in my slides a bit. So let's so here we go. So what I'd like to do is in the RStudio, I'd like to sort of develop this paradigm a little bit. So this is a nice a diagram which I've really grown to really realise the significance of and the importance of, which is a diagram which explains the kind of methodology that's been adopted in a book that's forthcoming called R for Data Science by Hadley Wickham and et al. And this book is also another book that's freely available online. So if you go to the website here, you can see the contents of the book in HTML format, or very nicely presentable online. I think it's a book that's going to be published next month in the O'Reilly series. So I think this is also an extremely nice book. It's more hands-on with the R, involving different aspects of R and data science. So I think this is a really good time to be learning about tools for data science, because what's happened, I'd say, in the last decade or two is that various packages, R and before that S and S+, and various other packages like to do with Python or to do with MATLAB, all of these packages or systems have been developing tools for data wrangling. And I think there's been a lot of progress in the last few years of tools which are simultaneously easy to use but also very powerful. And I think this is a new thing, that in the past the power was only available with the tools that were not very easy to use. So I think it's a very exciting time to be learning these things now. And certainly this book is going to be a seminal contribution, I think, in this area. And I'll just maybe spend a few moments talking about a couple of slides. So talking around this picture here, so the idea is that, well, with data you need to have means to import data, perhaps in large quantities, into your system. So that may be functions to read from CSV files, or to read other ASCII text file formats, or it might be to open channels to communicate to databases, for example, SQL databases or other types of databases. Or you might have tools which are communicating maybe over web protocols to web servers and extracting data or streaming data from other sources across the internet. So all of these things are enabling you to import data. And then this operation, so-called tidy operation, is one where we kind of take lots of data, which is often messy and awkward to deal with, but we tidy it up. So we have sort of a strong notion about what that tidy format should look like, and we kind of make it consistent, and we use that tidy format. And the book talks a lot about this and gives you, in fact, an R package with some very nice functions which help you and assist you in doing that. And I think that's very good because it gives us a sort of common conceptual format to think about our data, rather than having to think, am I of this type or that type? Well, no, we always stick with this type, don't we? And we can always convert it to that type because we've got the tools to do that. Then in the middle is the set of important boxes, so transform, visualize, model. So transformation might be to take some of our variables that we've imported and tidied, take them and change the units or combine them by adding or apply some functions to one or more of the variables. So often we'll want to do those sorts of transformations. We need to have the tools available to do that. Once we've done that, then we might want to visualize, so produce some sort of graphic or animated graphic even of what we can now see in this transform set of variables. And that's very useful because it helps humans ask questions about the data, helps you discover structure within the data by having a potent and helpful visualization of the data. And it will suggest maybe new transformations or in fact new data that might be useful to help explain what was going on in a visualization. So it's something that's provoking. It engages the data scientists with the data, gets us to think about it and engage with the data. On the other hand, besides the visualization, there are also modeling activities. So in modeling, you ask a precise mathematical or computational question about the data, and you derive results according to that precise formulation. But often that comes sort of secondary to having visualized the data. Having visualized the data, it might be screaming out to fit a linear regression model or some other parametric regression model, and then we go away and do that. So modeling is a sort of a distinct but not incompatible activity with the visualizing. They kind of go hand in hand. And so there's this kind of virtuous circle here of transforming the data in various ways, producing visualizations which then spur you to look at other models. And the purpose of all that is not just to use up CPU cycles and play with R, but it's actually to communicate our thoughts and our findings about use of data, be that in the pictorial form with the graphics or the precise mathematical question, precise modelling activities we've done, and then communicate those things. So this is where I think RStudio is quite good in having these notebooks which make it very convenient to sort of package all this up together and then hand it off as a report. So I think that's very important. Okay, okay, so maybe what I should do is just quickly have a look at RStudio, and I think we'll probably be due for a little break. So let me just switch to RStudio. So RStudio, I'll just spend maybe 2 minutes doing this, and then we'll break, and then we'll come back and do lots of this. So in RStudio, unlike the just the regular R download, which gives you a console window, which would be a window here with an R prompt where you type the R commands. What RStudio does, I think, very successfully is it gives you a set of multiple panels all within the same application, which enables you to do things that are quite tightly connected. So, for example, you've still got your console window. You can drag all these windows around and so on. Okay. In the regular R system, if you produce graphical output, then it will pop up a window, or it will send the graphical output to whichever graphical channel you've established. Here you have another panel inside RStudio where the plots will be assembled, and you can do various operations on that to zoom and to save it and so forth. And also, in addition to the console and the graphical output, you also have what they might call an editor window, and the editor window perhaps is containing R source commands, which you can edit, and then you can selectively execute them in the console. So you can sort of copy them across and execute them in the console. It gives a very nice, convenient way of keeping your R commands and functions in a nice editor context, but also seeing the output from them. That's if you're editing a regular R file of commands, but you can also edit these what are called notebooks, or indeed you can edit documents, as I've been doing with my slides. In fact, you can edit them where they contain a mixture of textual information to fill out a report, interspersed with R snippets which get executed to get the results and to draw the plots. So we'll see examples of that in due course. So there are sort of three main panels, together with other ones which will occur at various times. But there's a console panel, an editor panel, and usually this is a plot panel. Alternatively, if you look at help pages, then it can show the help page in that panel. You can sort of switch between it according to the tabs at the top. What I'll do is I'll spend a few minutes talking about this idea of tidy data sets, and which is the sort of precursor to this transform, visualize, model paradigm, and then we'll switch back to the RStudio and give practical examples of these things. So let's think about this tidy data. So if we think what is the ideal for a data set, well, it contains values, and those values can either be continuous variables, quantitative information, or they can be categorical, so discrete type variables, two sorts of variables. But in any case, they're values, and each value belongs both to a variable, that could be the height or the temperature and so forth, but also that value belongs not just to a variable, but it also belongs to an observation. So an observation could be the person, the day, the event where the set of variables was measured or obtained. So with that in mind, the idea of a tidy data set is one which obeys these three principles. And these, if you like, if we can, we kind of rigorously insist on these three principles. So the idea is that each variable forms a column in our matrix or data frame. So variables can always be found by thinking about what are the columns. Each observation will be a single row in our matrix or data frame. So we know where to find observations, they're given through the rows. And each data frame or matrix refers to just one type of observational unit. So we don't try to mix things up in the same data frame. So if there were distinct experiments or measurements of distinct quantities, distinct from, say, the measurements we were taking in our experiment, or just sort of background metadata, all sorts of things, then we put those in separate tables or data sets of their own. And this sort of set of principles rather closely mirrors, as a kind of statistical variant, of the principles that were outlined by Edgar Codd in his early work in the 1970s on database theory, in particular relational database theory. So in that theory of databases, there was so-called third normal form, 3NF, which were very similar types of principles to these types of principles. And this sort of discussion around variables as columns, observations as rows, and so forth, is one that's very nicely described in this tidy data paper by Hadley Wickham. And he's an excellent author in this area, but also is an excellent author of R software in this area. And I'll be talking a lot about the sorts of software that he's produced, he and his colleagues have produced. And in particular, the book I referred to just a while back, the R for Data Science book, is by Hadley and his colleagues. Edgar Codd, I don't know how much you know about him. He's a British computer scientist from Oxford, I think, and he's a Turing Prize winning computer scientist, so I thought it was worth noting that in this venue. I think 1981 Turing Prize for his contributions for database theory, while he was, as he did through most of his career, at IBM in the US. So there's a reference here to Codd as well. Okay, so that's the kind of clear but strong principles for a tidy tidy data set. For example, if we had this data frame in R, let's call it messy, this data frame has 3 variables. It has a name, as shown here, and then values under column A, values under column B. Well, this is quite messy because we are not sticking with those principles of tidy data. Perhaps these are measurements of heart rate according to those individuals, whether or not they had treatment, say, A or treatment, say, B. So all the variables and all the observations are kind of muddled up, as shown in this messy data frame. But a tidy version of the same data would instead structure it as follows. So every column is a variable. There's a variable which is the name. There's a variable which is the drug treatment, either A or B. And there's a variable which is the heart rate, according to the person and the drug. And each of these is an individual observation of their heart rate with that drug. Okay. So the semantic description of the data is completely aligned with the structure of the data. So the semantics is telling us what we need to know, and the structure is the columns. Okay. So it gives us a much cleaner way of representing information. And it's much easier to communicate both with ourselves and our colleagues, but also with computers, what is this data set referring to. Okay, so this would be a nice example of a tidy data set. And going from here to here might look kind of easy and trivial in this rather small example, but doing it in a large context, a large data set context, rather than fiddling with your own low-level commands to do that, then there's a package, I guess it's called tidyr by Hadley Wickham and co, which gives you a few simple functions, a few simple tools, which will take you straight from messy to tidy. And these are well worth learning and becoming familiar with, because then we can talk in this tidy data set context. Okay, I'm not going to spend the time now to look at the tidyr package, but I encourage you to get familiar with that. I guess this is a knitr presentation, so here was some R code, and I just listed that data frame. Here's a new data frame. I didn't say how I got that, but there was a little use of the tidyr package to transform that to that, using, I think, the gather function in the tidyr package. So it was all completely automated, going from messy to tidy. Okay, so as I say, this package, the tidyr package on the CRAN site for R packages, gives us the helpful tools to manipulate many types of messy sorts of data into tidy data. And it's a nice quote from the tidy data paper. It says, tidy data sets are all alike, but every messy data set is messy in its own way. I think that's a nice way of summing it up, that once you've got it into that tidy data set, then it's readily interpretable. The semantic and the structure have aligned, whereas messy data sets are just complicated. Of course, that tidy, those 3 principles, that tidy data set, is, what I'm stressing, is very useful for working with R and for analysis of data. It may be that it's too verbose to list it like that, and let's say in a sort of academic paper reporting a data set, one might be much more ambitious and have much more complicated structures to represent the data. But that isn't the right way to work with it for doing computer analysis. It's the right way to communicate a sophisticated story in a detailed analytical paper. So I think separating those out and keeping your data sets tidy is a really useful thing. So things that messy data sets have that tidy data sets won't have are, you might have that column headers are in fact variables, like the A and the B, as we saw, the values, sorry, like the A and the B in the earlier example, rather than variable names. You might have multiple variables all in one column, and you need to separate that out, so a single variable is a single column. You might have variables that are stored both as rows and columns. You see that sometimes. You might have different sort of experiments all bundled into the same data frame. That can be awkward to deal with. A single data set should have a single observational unit. And sometimes a single experiment gets spread off into different units, and that's not convenient either. Okay, so that's the idea of tidy data sets, and I think the tidyr paper, the tidy data paper and the tidyr package give us the sort of the motivation and the understanding of that problem, and also the tools to remedy that. A second package, which I'd like to probably spend most of our time talking about is one which I think is now excellent for doing these sort of data wrangling tasks. So this is the package dplyr. It's not an easy name to remember. It's got something to do with data frames. It's got something to do with applying functions to those data frames, and it's an R package. But in that package, I think you've got a very strong set of tools which are really quite straightforward to use now, which give you actually a very comprehensive range of tools and facilities to do data wrangling, as we say, where data wrangling is that idea of tidying and transforming data. So the main functions offered by this dplyr package are given here, and they're sort of basically 5 or 6 verbs which are actions that you might do to your tidy data frames. And I'll summarise a list of them here, and then we'll look at them in action on the RStudio. So filter is a function offered by that package which allows you to extract rows from a tidy data set. That's to say, it talks about extracting one or more observations. And you can filter according to various sorts of Boolean expressions about the other variables in the data frame. So in fact, quite complicated Boolean expressions, which are quite easy and natural to write in the filter function. There's also a function called slice. So filter is sort of set up to do matching on a Boolean expression as to whether to include or exclude a certain observation, let's say a certain row, whereas slice enables you to slice a subset of rows by number. So you can slice off the first or the first 5 or the second and the 5th or something like that. So rather than by context with other variables, it's by position in the data set. So that's a very useful function to be able to operate on the basis of observations. A range is just their term for sorting. So we can sort the order of the observations according to various variables in the data set, and we can sort them ascending or descending, and with several layers of variables. So you can give sort on the first variable, and then within that sort on the next variable, and so on. So for a range, read sort. Okay, and then select is similar to filter, except it selects on columns rather than on rows. So with select, you can select which variables to retain in the data set. So it extracts some or all the variables. In doing so, there's a limited facility to rename the variables, which may be convenient to do when you select them, or there is a function purpose-made to do exactly that, called rename. So you can just change the names, tidy up the names of the variables. And then there's a couple more. So distinct is an operation you can do on a data set which will extract just those observations for which one or more variables are distinct. Okay, so it will collapse down duplicates into just the distinct cases. Okay, and then there are 2 more which I think are really important to get familiar with, and we'll see examples of them as we go. So the mutate function, what that does is it takes a tidy data set and it mutates it by adding additional variables, and those additional variables are constructed as functions of the existing variables. So you can have a new variable which is sort of kilometres rather than miles by applying the transformation function on that variable, or it could be a transformation which involves several variables which you combine together through a function to produce a new variable. And when you mutate, you can add in one or more additional variables, and also the way in which you describe those additional variables it's a lazy evaluation. So what that means is that you can create a new variable in the mutate, which you can then use in an expression in creating another variable. So that's very convenient to be able to express things like that. So mutate builds new variables out of existing variables and then adds them in as additional columns. Transmute is like mutate, but it doesn't add them to existing columns. It just generates a data frame with only those new columns. Okay. you could get the effect of transmute by doing mutate and then selecting just the new columns if you wanted to. Okay. So mutate takes observations across the rows and it builds new variables in addition, whereas summarize will take a data set, a tidy data set, and it will apply an operation to that data set to summarize all of the, let's say, the mean of one particular variable or the mean of several variables you can summarize. So it produces one number for the data set, or one number per expression that you put in the summarize. So you can extract means of various columns or maxes or mins or other functions that you apply. So summarize is one where it focuses it down to one number or one vector of numbers for all the rows in the data set. And then there's an important twist to that, which is that, as we see here, there's also a group by operation. So what you can do is take a tidy data set and say group by one or more variables, and then the various actions that you take, for instance, the summarize action, is always done per group. So if you do a group by which produces two or more groups within your data set, then summarize applies to, let's say, extract the mean per group. So if you've got men and women, you could group by gender and then get an average for men and an average for women. Straightforward like that. And this is a very powerful tool which is used a lot in this DPLYR package. And then one more here is just sample n. So the sample n will take a tidy data set and it will produce a random sample of, say, 10 observations if the argument to sample n. So n is sampling a fixed number. So I want to have a random sample of size 10, for instance. Similarly, sample frac produces a random sample where you specify not the number but the fraction. So if you want a random sample of 10% of the observations, you can do that with sample frac. So those are the sort of main actions you can do with the DPLYR package. And then crucially, as this package has evolved, it's evolved, I think, into a very nice sort of easy and powerful little language for building pipelines for data wrangling. And the crucial thing that makes this work is that you can chain together these operations to produce pipelines. So there's a special operator which allows you to chain one operation as a successor to the previous operation, and so on. And this, I think, is really useful if you're familiar with other languages like I know, F# or OCaml. You can have a pipe operator similarly there. Similarly, you can build a pipe operator for Scala if you like Scala, as I do. And this gives us a nice way of chaining things together. Okay. So what I'll do now is to switch over into the RStudio and give you a sort of run through, a walkthrough of using these types of facilities. So you'll probably forget them between now and when I talk about them, but actually there's only 4 or 5 that you need to remember, so very quickly you can sort of get up to speed with quite a powerful set of tools to do data wrangling. Okay, so let's switch over to RStudio. So if we go back to where we were before, and as I say, this is the console, this is the editor window, and this is used for other things, for example plots, when we produce plots. So what I'm going to do is to edit a file of R commands, and that will be assembled as illustrations of this DPLYR package. And as we edit it, we'll execute lines selectively and they'll be edited in this console window. So I'll make the console window a bit smaller and concentrate on the editing. Okay. So if we open a file which is going to be this file here, then inside this window I've now got laid out a number of R commands, and we'll sort of have a guided talk through of this discussion here. Okay, so are you able to see it at the back? I think I can make it larger. Okay. Oops. Oh dear. Okay. And I have to say I've only recently myself switched over from using the usual R console to this RStudio, and so I'm very used to there being only a single window to type in, which is the console window. And so I'm not used to having these separate windows all nicely together in this RStudio environment. So I often type in the wrong window, is what I'm trying to say, and you'll see many examples of that. And that's because I'm not used to there being a possibility of a cursor being in two different places. Anyway, my cursor at the moment is up here, and the first step, I hope you can read all this. So the first step is to load a package which is called the tidyverse. So it's a sort of pun on universe. It's a universe of tidy related packages. And tidyverse is, if we execute it, which I do, that's that. So there it's executed in the console, it's scrolled off, and it's loaded a number of different packages, the ggplot2 package, the tidyr package, the dplyr package, and a few others as well. And what I'd like to do is to, so that's made those different packages and all their associated functions and datasets available in the session now. I'm going to load another package called NYC Flights 13. So this is contains several datasets relating to tidy datasets relating to, in fact, a comprehensive archive of the lists of flights out of the three New York airports, so JFK, Newark and LaGuardia airports throughout the year 2013. So if I load that, it worked. This is a package, again it was put together by Hadley Wickham, which you can get from the CRAN archive. And if you go to the CRAN archive, you get a nice page describing each package, what it depends on, what it does, the source code and all the things. But often there's a link to a sort of a website which gives background information about the package, or it might be a GitHub repository site. So if you go to the GitHub repository associated with this package, you can see the tools that Hadley Wickham had used to actually download this data from various repositories of data in the US on flight information, and it shows you how you can build that for the year 2013, as he does in this package. But you could go back and use his tools to build the information for 2014, 2015, and so on. And you can see exactly how the package was built and how the data was tidied up, as we say, to produce this set of data frames. Okay, so just to quickly look at what's going on then. So within this package, NYC Flights, there's a data frame called flights. So I can take its dimensions. So dim flights says it's got 336 observations, 336,000, rows, and 19 columns. And if we just look at the head, so the first few observations, then we see has this form here. Scrolled off the screen a little bit. Just open that a little. So actually what's happened here is that the flights data frame has produced something which is in a slightly more stylized format than the regular data frames, and these are called tibbles. One of the tidyverse packages was a tibble package. So a tibble, I suppose it's a pun on table, I suppose, is a sort of variant on your table, and it makes it a lot more convenient to work with big tables. So I think if I said flights without the head, so if I just type, yeah, I get a similar thing. Okay, so a convenience method for printing a tibble rather than a regular data frame is that it will effectively run a head on it and only produce the top few rows. Now, you might think that's trivial, but when you work with large data sets, it's very easy to just say, I'll look at it, and you're not realizing that there's 336,000 rows. And when R prints that, it gives up after a little while, but it will be lots of screens worth of junk. So it's a bit, but it's very nice to have that convenience to just take off the top rows automatically. Of course, you can override it if you want to see a larger portion of the data. Another thing it does is it tries to not crowd out what the information is that's being produced. So it produces a number of variables sort of fitting across a screen, but then it says there are also additional variables, 10 more additional variables, which I haven't shown, and these are the variables. With the select operation, you can select columns, so we could easily get us to view those variables as well. But it won't give you, as regular R does, it gives you a sort of wrapped round line, which is really impossible to read after a while. So it's much more user-friendly, I think, like this. Okay, so we see that the flights data set has a year, a month, a day, a departure time. Move that up a little bit. Actually, the departure time is in a sort of coded form, so you can see this perhaps easily by looking at the GitHub website where these quantities were structured. So this is 517, which means 17 minutes after the 5th hour.
Please go to reception. Would the building manager please go to reception?
Okay. So what have we got? We've got the date information. We've got departure time in this rather unusual format. So that's the actual departure time. We've got the scheduled departure time, the departure delay, so it's delay on departure time. Then you've got the arrival time, the actual arrival time, the scheduled arrival time, the arrival delay. This is in minutes, so that can be positive or negative according to whether you arrive early or not. And then some of the other variables are a string identifying the airline carrier, the flight number, so the route number, the tail number of the aircraft. So if you're a bit of a aircraft fanatic, a bit of a plane spotter, as I am, then you've got the actual tail number. That's the registration number on the tail at the back of the plane. And there are additional data sets that allow you to drill in to see what type of plane that is. You've got the origin airport, the destination airport for the flight, the arrival time, the distance. Not sure I remember which the units are, but you can look that up. And then you've got the hour, minute, and the time, hour quantity. So time and hour together into a date time object. I guess the other way to think of it is if you say, I guess if we say library help equals NYC flights 13. Okay, so up in this window here, which I think I can make bigger by doing that, then it tells us the sort of rubric about the package itself, the authors and the versions and so on. And it says there's a sort of index of things that the package gives us, and it gives us this flights data set, which is the one we've just been looking at. There's another one associated with the metadata of the plane, indexed by that tail number. There's hourly weather data across the year 2013. There's a metadata about the airports for the origin and destination, and also the mapping between the carrier labels and the usual expanded full name of the airline. Okay, so I'll bring that down again. Okay, so tibbles are a nice sort of addition to data frames, which are just more convenient to work with, especially for large data frames. Okay, if I go back to my file up here. So here's some examples of using those DPLYR verbs to take actions on data frames. So the first few are the filter. So filter, in the first argument it takes we just run that. So filter takes the data set, the flights data set, and then there's a comma separated list of Boolean expressions which are ANDed together, and then you select the rows for which that Boolean expression is true. So that says we can say that month equals 1 and day equals 1 to select flights only on the 1st of January. In usual R, when we build a Boolean expression to extract things, we probably have to put the ands in ourselves. Obviously you can do, as in the second example, as shown here. So this might be the regular R way of doing things. From the flights data frame, we index all those rows for which that is true, and then every column. So this is the rows for which flights month equals 1, flights day equals 1. So obviously that's very cumbersome to have to write out compared with the DPLR version. If you want Boolean expressions other than AND, which is the common case, if you want, say, OR, then you can build them yourself, as shown in this example here. Okay, so that's where month is equal to 1 or month is equal to 2. So comma separated list builds a AND between the Boolean expressions. Okay, and again with slice, that will slice off the first 10 lines. So the sequence 1 to 10 is the rows that are sliced off from the flights data set. Okay, if we go to here, so with this arrange, we'll do a sort. So we'll sort the flights data set by year, by month, and by day. Okay, very easy. And this is the way you can modify the sort order, is if you surround one or more of the variables by this function DESC for descending order, then instead of the ascending order, which is the default, it puts it into descending order for that variable. And you can do that for one or more of your variables in the sorting order. Okay. Okay, and the next one is this select. So select, if you recall, it will select one or more columns, that's to say one or more variables, and give you the selected columns only in the output. You can either name all the columns, or you can name all the columns between year and day by using the colon separator. And you can also select all the columns except a certain subset with the minus sign. So you can select from the flights dataset all the columns except those between year and day. So you've got a reduced number of variables that way. And there are other ways too of doing this. There's a rather nice collection of helper functions you can do, which will do things like select variables whose names start with this string or end with this string. All these things, quite useful. Okay, and then this example here is the rename, which is for convenience you can do the following. So rename allows you to take a variable and give it a new name, and then that's what's included in the output. So it's not shown here, but tau underscore num has replaced tau num. So distinct is going to extract from the flights data frame the tau nums, but only the distinct tau nums, which are given by this variable here. So this is the sort of thing you see at the back of aircrafts if you peer at the back of them before you take off. Actually, maybe I should have a little peek at that other data set. So planes, so planes is a set of attributes associated with the tau nums. So there are 3,322 distinct planes that were observed in this data set of all the flights in 2013. And there are 9 columns of information. So there's the tau num, which is a primary index on that. And then there's the year, presumably it's entered into flying, and then it's the type, the manufacturer, the model of plane, the number of engines, the number of seats, and the speed. Sometimes it's not available, so it's NA. And there's one more variable, which is the engine type there. So you can drill down into looking at in detail about what types of flights are flown in what type of places. Okay, so let's have an example of mutate. So so if I execute that mutate command, which is given here, it's repeated here, that's the output. So mutate takes the flights data set and constructs some new variables which it adds on to the existing flights data set. So this mutate has added on two variables, one called gain per hour, and gain is this function of some of the original variables. So it's the difference between the actual arrival delay minus the actual departure delay, which you might think of as the gain that took place when you took that flight. And then gain per hour uses this new variable gain in the expression to form, this is the gain per hour of flying, so that's the arrival air time, that's the amount of time spent in minutes, divided by 60 is the amount of time spent in hours. So that's rather nice. You can build these variables using the new variables you've just constructed, okay, which gives us this thing here with the gain and the gain per hour new variables. And here's an example of transmute. So transmute, if you recall, is like mutate, but it gives you back just the new variables and not all the other variables. So transmute just gives us back this gain and gain per hour. Okay. So the complement to mutate was this summarize, where summarize, in this example, takes the flight status frame and it constructs a new variable called delay. And what it does is it takes all of the observations of departure delay and then constructs the mean of that, and that's called the delay. So there's one number which is 12.63, which is the average delay of flights. Now some departure delays are actually missing, so they're NA. So when you take the mean, if you didn't override the default, it would take the mean to be of that set of observations, one or more of which are NAs. It would just say the mean is NA, which is probably what you don't want to do. You want to remove the NAs. So if you say NA.remove equals true, then in mean, as in several other functions, if you do that, then it drops the NAs first and then takes the mean of the remaining variables. So that's a very useful behaviour to be familiar with. So the mean delay looks like about 12 to 13 minutes on our flights. In the following, so sample n is going to produce a random sample of n flights, n equals 10 flights from our flight. So it's a set of rows given by a random sample. There are ways to set the random number seed if you want to, and there's ways of overriding whether the sample should be with or without replacement. Okay, that's the sample n. Sample frac is given by this here, so this is going to produce 1% sample of a random sample of our flights, as given here. Okay, which has 3,368 rather than 336,000. Okay, so here's an example of the group by. So when I do group by flights and then the argument tail num, then it's going to take all the observations, look at the tail nums, and group according to the distinct values of tail num. That's to say distinct actual concrete aircrafts, as it were. Okay, and that returns a grouped by version of flights into a new data frame called by tau num. Okay. In the next set of things, what I do is I take by tau num, which is a grouped data set, and then I apply summarize to it. So when I calculate the count, the dist, and the delay, they're going to be per group. Okay. And then what gets returned back is returned into delay. So count is, well, sorry, let's do these two. Dist and delay are just the mean of the distance and the arrival delay for the flights, which are grouped by aircraft, flight num. And count, on the right-hand side, it's n brackets like this. So n is a sort of convenience function that's introduced. So n just says how many there are in that group. Okay. So you don't have to sort of do anything more clever to find out how many rows there are per group. You can just call the n function and it finds it for you. Okay, so if we have a look at delay, then so delay here has got the different tau nums, and it's got the distance the count, the distance and delay per tau num, because it was a group by summarise. Okay, and so what I'm going to do is to sort of draw a plot of these delays that we've just calculated, and it's an interesting feature of these delays, if one looks at them, that we get some outliers. So, for example, some of these delays have a count which is below 20, so we'll kind of ignore those. Let's look at the ones where the count is more than 20. And also some of these distances flown are excessively long, so let's filter out those as well. So let's say distance less than 2000. So now delay has been modified to be just those observations for which count is more than 20, so there's a prevalence of observations in that tau num, and distance is not too great. So if I go back here and then do a ggplot command, then there's the plot over there. So what we're doing here is we're taking this delay data set and we're doing the aesthetics where x is the distance, so that's the horizontal quantity there, y is the delay, which has just been calculated for us here, and we're adding to that the points, and the points have well, they have not just an x-y position, but they have a further aesthetic associated with them, which is their size. So the points are individually sized according to the count value, and so that's an aesthetic relative to these points. And these points also have an alpha, so this is if alpha is half, then they're slightly greyed out, halfway between 0 and 1. So you can give them a sort of an alpha channel value of a half. You can add a smoother on as well, as shown here, which suggests that delay as a function of distance is complicated. So short flights can get quite substantially delayed, but some of these longer flights, there's a bit of a bump here, some of these longer flights have more modest delays. So maybe the airlines give priority to scheduling things to keep these things a bit more on time, or not to let delays grow with distance. And then the so the scale on the side here is just given by this area scale associated with the size aesthetic. So it's a scale that's being put on which labels that for you. So there are different sizes given here according to the different values of the count. Okay. So I'm sure there are lots of features of this plot panel, but I know, for example, plot zoom allows you to pull off a nice flexible panel with the plot in if you want to. Okay, and I guess there are other ones of flipping backwards and forwards between your plots using the arrows. Okay, so where do we get to? Yeah, so I think I'd like to illustrate one further thing, and then we might even be due for another little break. Let's see. Let's suppose that we wanted to do the following combination of operations. So let's look at these lines here. So suppose I take the flights data set and I group it by year, month and day. So all the mutates and summarise will all be per group, which is effectively per day, under that year, month, day group by. And let's save that in A1, and then we'll select just the two columns, arrival delay to departure delay. We'll call that A2, and then we'll summarise it by adding in arrival and departure means, as shown here. And then maybe in A4 we'll pass A3 through a filter to extract just those observations for which arrival is more than 30 and departure is more than 30. So or those two. So if I do those commands, I think you can select a number of lines and then execute. So if I do all those things, it builds us all these A1, A2, A3 and A4. And a lot of data wrangling tasks end up building lots of temporary data sets like this. And it gets messy. You have to think of a new name each time and you have to keep track of all these names. It's a bit of a inelegant way of presenting things, although lots of our code is done like that. An alternative to that would be to use the method shown here. So what am I doing here? Well, I'm sort of embedding them in this big nested list. What am I going to filter? Well, I'm going to filter the result of the summarize. What's the summarize? Well, it's applied to the select operation, and then the summarize has these two arguments in addition to the select operation, and then the filter has these arguments in addition to do the filtering. So I could do that and I get the same result. But the drawback of this is that essential parts of the filter are listed right down here, a long way away from the action name filter, and similarly for the summarize. So it hasn't sort of got the right locality to it. It's a difficult way of expressing things, although it's to some people who like to nest their lists like this, then they're very readily able to do so. But I don't think it's the most natural way of building this. It's not as natural as this way, but notice it hasn't got lots of arbitrary temporary variables along the way. So what we'd really sort of like is the best of both worlds, okay? And that's what I think this package gives us now with this chaining operation. So I can get exactly the same effect by the following. So what this does is it takes expressions and it produces a new binary operator to act on pairs of expressions, and that's the operator which is percent angle bracket percent. So that triple, that 3-character expression, is a binary operator, and the left-hand side is the flight's data frame, and then what it does is it takes that and it uses it as the first argument into the expression on the right-hand side, which is the group by. So this is a way we can now chain things together. So flights becomes the first argument to group by, together with these arguments, which is now the left-hand side of the next expression, which gets piped through as the first argument to select, which also has these additional arguments. The output of that is then moved to summarize and then to filter. So with that convention that the first argument to your verb is what you want to get piped in from the left-hand side, then this all runs together very nicely and smoothly. You don't need to have any temporary variables, and the filter operation is just specified in one place rather than spread around two or more places, often very far apart. So this chaining together is a really nice way of building these pipelines, and this operator, let's see if I can do this. So how does the operator work? It's so if we were doing a function call f of x, y, then what it's saying is that we can replace that by x percent angle percent f of y. Okay, so we type that, and the effect is to call the f function with the left-hand side inserted in as the first argument, and then the other arguments as well. Could be y or y1, y2, and so forth. Okay, so that's this operator here, and that's a very powerful tool which is used very effectively in this package and in many other packages now. This is becoming the sort of preferred idiom for expressing these things and building pipelines, so it's, I think, going to be used in more and more R packages. So it's very nice to see. There is some variance to this, but I would definitely encourage you to start using this. There are, I think, a couple of additional ones. So I think you can say double angle bracket, and that does the following. So if I say x, f, y, then with the double angle brackets, it's effectively doing x becomes x percent f of y. So what it's doing is, in addition to this, it's also doing the extra assignment, which says assign the final result to the left-hand side, the original left-hand side. So you might put that as the first chaining operation in a long pipeline, which just says all these pipelined operations will augment the left-hand side here into the final result. Okay. And I think there are a couple of other extras as well. If you don't like this or find it inconvenient to have this idea of replacing the first argument, then there's an additional notation which is that on the right hand side, if you put a dot in a position for an argument, then it's replaced by the left hand side. So this is effectively, if I can just repeat this, so this is effectively saying x f dot y. So it's being more expressive. It's saying I want x to replace the first argument. But of course you could put the dot somewhere else if you really wanted to. You put it to the second argument, and then it would have the effect of inserting the left-hand side at that position rather than the first argument. But the first one is the default, and so you can leave out the dots. So that just explains sometimes you'll see the dots, because what they want to do is to override where that left-hand side gets inserted in the expression on the right-hand side. Okay, so this is the one to learn. That's the most important one. The dot is a little extra thing, and if you get fed up writing this left-hand side, right-hand side assignment all the time, you can be very sophisticated and use that operator in the first position. Okay, I'm sure there'll be extensions to this package which will build this out into more features. Okay. So I think now might be, well, let's just do just a couple more and then we'll have a short break. Okay, so another data set which is provided through the DPLYR package is one called MT-cars, which is shown here, which is a data frame which is not in tidy format, by the way. You can see it's got row labels for the variable which is car type, and it's got other variables in the columns here to do with miles per gallon, number of cylinders, the displacement, which is basically the engine size, and then the various other things like the weight and the number of gears and the carburetor and so forth, numbers of carburetors. MT, I think, is Motor Trends, which is a magazine on cars. I think these cars are quite historic cars. I think they're 70s cars, I think. So it's quite fun to have a look through there. But if we just take a look at this pipeline that I've built here. So we take this data frame, the MT cars one, and we pipe it through. So one of the functions in the tidyr package is this row names to column. What it does is it observes that there are row names in this data frame, and it builds a new column, actually, whose name is model type. So what variable should we introduce? Let's call it model type. And it adds in a new variable, strips out the row names, adds in a new variable called model type, which is given by these row names. So if we pass it through row names to column, we'll tidy it a little bit, removing the row names and make a variable out of it. And then, because this was actually a data frame rather than a tibble, we can pass it through the as tibble command, which will take data frames and force them to have this tibble attribute as well. So that will tidy them up no end. Okay, so MT cars has been modified to this tibble arrangement. So if I look at MT cars, we'll see it just produces the first few rows, and it gives the type for each of the variables. It's introduced this new variable called model type, which was previously the row names. Now we don't have any row names because that wouldn't be a tidy data set. And it managed to produce all the variables across the page like that. And let's do one more. So if we take our tidied up version of MT cars and we do the following, then this tidier data frame becomes the data to an LM call. So we use the dot notation, as I've mentioned, to say that this left-hand side becomes inserted with the argument data to LM, and the model formula for the linear model is going to be a response variable MPG and weight as the predictor, and the saved output from that we'll call LM fit. And if we do summary LM fit, then we'll get all that information there. So summary LM fit reminds us of the call that we use to produce the model residuals, the coefficients, the standard errors, t-values, p-values, and some other information like the r-squared is printed there. This is similar to the summary you get from various other types of model fitting procedures in R. So, for example, there's GLM, which is generalized linear models, and so on. And it gives you lots of information, and from the summary you can extract, as we did before, the coefficients and so on. There's a nice package that I'd just like to illustrate now, which is the package called Broom. So if we load the library Broom, what this does is it, so along with tidy, it sweeps up all our information and keeps ourselves very tidy. And what it does is it gives us some several functions. There's in fact tidy, augment, and glance. And these three functions, if you apply them to the result of a model fit, for example, our LM fit, then if we apply tidy to that, so if I apply tidy, then what it does is it gives us a data frame. It's taken the same information we get from summary, but it's arranged it in a tidy format. That's to say we've got different variables as columns, and the different variables describe the different information about the estimates in our parametric model of the linear model. What it does is it gives you a way of assembling the information, which is all buried in this summary, in a nice tidy format. And that's very useful if you do a lot of model fitting, perhaps with different parameters. You want to scan or build a grid of parameters. You can get the tidy versions of the model fits in this way, which allows you to assemble them into a tidy data set, which you can then group by, mutate, and draw plots and so forth. So tidy is very nice in removing the clutter and just giving you a tidy version of some of this information. If we look at augment, so if I apply augment to LM fit and then just look at the head of that, so the first 6 rows of that, what augment does is it takes the LM fit, which has got all the information about how that linear model was built, including the data it was used and the parameters and the model formula and so forth. What it does is it then takes the data and augments it, as it says, with some additional variables. Let's say it runs mutate to add variables. And the variables are, well, they all start with a dot to show that they're new variables that have been introduced by the augment. And it gives you the fitted values under the model, the standard errors, the residuals, the influence hat parameter, so various other modelling parameters associated with that linear model. So it's a way of quickly attaching the fitted and the residuals to the primary variables in the model. That's a very convenient thing to be able to do, to then draw plots of residuals against fitted values and so forth. So augment is very useful in capturing that information into a data frame. Whereas glance goes in a sort of different direction. So glance of LM fit gives you a one-line summary of that linear model fit. It gives you things like the r-squared, the p-value, and the degrees of freedom, various other quantities, statistical quantities associated with the fit. So that's a good way of summarising your model fit. That's done by glance, whereas augment builds out the data frame with all the fitted values and residuals and so forth, and tidy just gives you the parameter information in a nice tidy format. So those three are functions introduced by the Broom library, which I think is due to David Robinson. So if I give just a brief use of that here, so if we take our empty cars and then draw a plot of miles per gallon on the y-axis and weight on the x-axis, do a point for each data point, and do a linear model smoother with standard errors shown, we get this type of information here. So it looks like the miles per gallon of these vehicles declines rather significantly with the weight of the vehicle, not surprisingly. Okay. Here's a more elaborate model. This one passes the MT cars as the data into a linear model, which is miles per gallon, where the formula is now predicting using the weight, the displacement, which is the engine size, and the number of cylinders, which is a categorical variable. So if we do summary of that, then here are the estimates and the standard errors and so forth for these different quantities. Notice that this p-value is large. These values are small. Let's say they get 2 stars, so they're between 0.001 and 0.01, whereas this one is large, it's about a half. So it's saying that on that basis, that's so large that the display quantity could have a beta coefficient which was essentially indistinguishable from 0. So maybe we would drop that from our model but keep the weight in the cylinders. If we look at the tidy version of that, then the same information is then arranged in columns usefully like that. If you say predict to a LM fit, then without any other arguments, what predict does is it returns the fitted values, just as in the column in the augment data frame. But predict also has an argument called what's called new data, but it's the second argument. So if we do the following, what we can do is we could do a prediction using our fitted model, not with the data that we fitted the model with, which just then returns the fitted values. What we could do is to give it a new data frame with some a new row in our of information. So what would a car whose weight is 4.5, displacement 300 and 8 cylinders, what would we predict under our model? And the answer is 12.70, 12.71. Okay. If we'd had more rows in this data frame, then we will get our predictions for each of those different predicted observations. So if you're familiar with the sort of usual paradigm of training data set and test data set, this is a way of introducing new test data to apply to your fitted model. So this is test data, this is the fitted model under the training data set, and this is what we get under that. I think there was a question. Yeah.
Does the package also work with other model, like instead of just the linear model, like your GLM?
Yeah.
Would that work as well?
Yeah. So the Brum package, which gives the tidy augment and glance, that works with quite a wide range of R objects corresponding to the output of different model fittings. So LM, GLM, and so forth. I can't remember the complete list, but I think the complete list was quite long and growing, and you can contribute new ones too. So you could build out your own versions. You could tailor the Brum library to work with a new model fitting of your own design, for example. Similarly, predict knows how to do this prediction operation not just with linear models, but GLMs and many others too. So predict is sort of like the standard generic term to do the prediction with test data and a fitted model. Yeah, so good. So these packages are becoming, you know, the lingua franca, the universal way in which we express this prediction idea. And similarly for the summary ideas. Okay. Okay. Now, what I think I'll do is I'll use the remaining time to talk a little bit about our notebooks and the way in which we can produce this sort of kind of reproducible research where the R and the markup are simultaneously stored in the same file. There are a few more examples of DPLR in this file, and I'll make this available to people. So there's a bit more, but it's I think it's probably better if I switch to look at the markup type things, the notebook type things. Okay, so let's dispose of that, and if we open another file, so here I've got a file, and this file was created within RStudio. I'll show you how to do this, but let me show you the sort of high-level idea. So the high-level idea is that we're now editing a file which is not just R commands as we had before. It's a file which is in R Markdown format. So this is a simplified markup language for documents, including examples of, say, R code or Python code or other sorts of executable code, which you can all blend in together. And what we're doing is we're editing such a document. And such a document, an R Markdown type document, is as follows. So these are plain ASCII files. They're very easy to send in email, to store and to edit in various sorts of ways. What they do is they have a format which is as follows. So at the top, between these three dashes, they have a sort of little bit of metadata that you can construct at the top. So the title of this document is Demo Report. The author is the name, the date, we've typed the date. And the type of document, this one is going to be called a PDF document. And there are other types I'll talk about in a moment. And after the header, which that's a brief header, you can have many more options too, which I won't describe here, but in the R Studio documentation for these R Markdown files, you can see the list of all the different header options. So after that header, then there are two things that follow. Either you've got text with R Markdown commands, for example, to give section headings and so forth, or so we start here with first reading some data, and then the other type of information you can have is a little snippet of code. And snippets of code are formatted in the following funny way. They have three open quotes, curly brackets, lines of text, and then three closed quotes, just to break them off from other text. And within the curly brackets, there's an R, which says that the language that the snippet is R. You could similarly have Python or many other languages that are, if you've got support for those. And then what you're doing between these, this prefix and this suffix is you've got lines which are R, which you're going to interpret. So in the document, if I click on the sort of green arrow that appears whenever you insert one of these things, it will execute that bit of R and build these two data frames. Data frame which is obtained by reading a data set which is called demo.csv, which was in the current directory, and then I've taken that data frame and I've turned it into a Tibble style data frame, so DF. Let's see, maybe I should just illustrate how you insert a new chunk. So these what I've called snippets are in RStudio, it's called a chunk, I should say. So this is an R chunk. So if you want to insert an R chunk, you can do so using the insert option here. So insert a bit of R, and it gives you this template here, and you can include a bit of R there, and if we execute that bit of R, then we get the output from that R, which is that 4 there. Okay, so I guess we don't really want that, but maybe we should. Okay, so so that was an R chunk there, which created the DF. And now some more text. I've just put now some exploratory analysis. I guess one should write a nice big opening paragraph explaining what your report is doing and what you're going to do. What I'm going to do is just to run the df command in R, which is going to then produce this output here. Yes, maybe I should just show on the console down here. Oops. On the console, the R chunks in the document, when I execute them, they're executed in the console. Here they are, and there's the output. So you can have a console version of the document, and you can add in your own commands here, which don't get littered into the document. You can just explore things here. When you've settled, then you can build them into the document. Okay, so in this, let's go back to this maybe. So if we look at this data frame that was included from the CS file, then there are variables ID, Y, X1 and X2, as shown up here, ID, Y, X1 and X2. And there are 100 rows there. So it's a Y value, an X1 value, and an X2 value. And from the summary, we see that the X2 values has a strong structure to it, whereas here X1 looks much more like a quantitative variable. And ID is just an index going from 1 to 100. Okay. So let's have a little explore of this. So if I execute this chunk here, I'll take that data frame with those various columns, 4 columns, ID, Y, X1 and X2, and the pairs command in R produces one of these plots. So let's execute that there. And what pairs does is it does the all pairwise scatter plots of the 4 variables. And so that's a symmetric object, so we can just look at the upper triangular part. So this is showing the scatter plot of Y versus X1. This is Y versus X2. And this is the ID versus each of the variables, which looks a bit scattered around. So if we look at X2, then it only ever takes 2 values, 1 and 2. If we look here, there looks like a sort of outlier data point for this value of x1. Y is ridiculously small compared with all the other values. And also maybe y as a function of x1 looks like it has 2 parts, an increasing part and then a decreasing part. Okay. If we look in this chunk here, then what this does is it takes that data frame and it draws a plot of y against x1. So the vertical aesthetic y corresponds to our variable y. The horizontal aesthetic x corresponds to the x1 variable. And all we do is plot a data point at each of those values, and we can see that there's clearly an outlier there. So what I'm doing in this document is little sort of trial, bit of exploratory data analysis to try and get a handle on how we could summarize the data in this CSV file. But it's being documented as we go along, both in text, in some R codes to do some calculations and transformations and their output, and also some plots. And it's all sort of connected in the same document, which ultimately we can save into a PDF file and hand in as our report. So if we just run a bit more R, we can look at the X2 column, df$x2, and the table command takes a vector and tabulates it. So what it does is it takes the x2s, which is just a big string of 1s and 2s, and it notes the following, that in the table is that there are exactly 51s and exactly 52s. Okay. So it looks as though x2 might be playing a role perhaps to specifying the left half and the right half. That might be a plausible hypothesis. So what I'll do is I'll just take the x2, since we've got equal numbers of x2 equals 1 and x2 equals 2, what we should maybe do is treat x2 as a factor. So that's to say we would summarise it as having 2 levels, either level 1 or level 2, and that you can execute by this command here. So take the x2 vector, turn it into a factor and save it into the x2 vector. So now if we do this plot here, what is this plot? This is the plot which has y on the vertical axis, x1 on the horizontal axis, but it has a further aesthetic, which is that the x2 variable, which is now a factor, which is 1 or 2, that aesthetic is turned into the colour associated with any points that we draw. So there's a little legend here, so red is 1, blue is 2. So if we overlay the colour, we can sort of see that x2 equals 1, except for a couple of rogue points here, is giving us the left-hand path when x1's less than 5, plus there's an outlier here. And then there looks like a rogue point over here when x2 is 1, and yet it's in the right-hand path. So maybe those are points that have been misclassified. Okay. So a bit more text. So we can see that there's an outlier around minus 100, and and also where x2 is equal 1. So let's find that observation. So let's filter df, will filter y, those values for which y is less than 50, and this is the data frame that comes back. So there's exactly 1 row after applying the filter in this little mini pipeline, and it looks like row 16. In fact, it's not minus 100, it's exactly minus 99, and these are the values of x1 and x2. So perhaps what we should do is remove ID 16 rather, sorry, and we can do that by overwriting df by filtering everything that is not index 16. That would be one way to do that. So that's going to remove this data point. There will just be 99 rather than 100 data points. I don't think any useful model is going to include that data point at the same time. Okay. Okay, and then there were those rogue points where x1 was less than 5, that was say the left-hand half, and yet x2 was equal to 2. So when we filter on that, we see that there are two observations with IDs 41 and 45. So they have an x2 which is 2, but they're in the left-hand half. So they're probably misclassified points, arguably, and maybe we can switch them over. So we'll assign x2 values of 1 where the ID is 41, and similarly where the ID is 45. That's a sort of quick way to swap them over. Okay, and now if we repeat the plot, we see the following. So that's tidied up. So two of those red points were previously blue points, and that looks better then. But there's still a red point, so let's sort that one out. Now, if we do that, so it is a similar operation. If I say, give me all those points for which x1 is greater than 5, so in the right-hand half, and yet x2 is equal to 1, then it comes back. In fact, there are 2 points. 1 and 52 have that property. I thought there was only 1 point when we looked at the graph, but in fact there are 2 points buried in there. And if we check the plot here and make the point size rather smaller than the default of 1, then we'll see, hopefully, in there that there are, maybe not too good on your screen, but on my screen I can see there's a red point here and a red point here, now that the dot size has been shrunk down a bit. Also, we could zoom in this part of the graph by a similar R plot where we specify the limits on the x-axis and the limits on the y-axis just to be that area there. So if we do that, we see this thing here, and so there's the red point and there's the other red point. So maybe the moral there is that you don't necessarily just want to have tools to visualize the data, you want tools to manipulate the numerical values so that you can decide correctly whether there are two points or simply just 1 point. Okay, so let me switch them over. So I'll set the x2 value to 2 where the ID is 1 and where the ID is 52. And if we check that, then indeed we have swapped them over. We've got them to be 2. Okay, and then let's draw the picture then. So we go back to this one. So this is all the points that have been cleaned up a bit. So the outlier has been removed. There are only red points to the left, only blue points to the right. So things have been sorted out a bit better. Let's try to fit some models to this. So I'll do that in the following. So what I'm going to do is take the data frame. I'm going to group it by the factor x2. So there'll be 2 groups where x2 is 1 and then where x2 is 2. Then I'm going to do another command here, which I don't think we've discussed before. It's another dplyr command, which is allows us to do more general things than merely mutate, which builds new variables with formulas using the old variables. So do takes an expression here which will in general return a data frame. What is that data frame? Well, that data frame is a tidy version of a linear model fitted with that model formula, and where the left-hand side of this expression is inserted through the dot operator into the data to the call to lm. And what is the linear model? Well, it's a sort of quadratic model that says that the response variable y uses predictors x1 and also x1 squared. If you use the hat operator for squaring inside a model formula, then it has a special meaning which is not what you mean by x squared. So you have to protect it in this I wrapper, so I for identity wrapper, which is a little bit awkward. There are many other ways of getting around that. But what this will do is produce a quadratic with a beta 0 for the intercept, a beta 1 for x1, and a beta 2 for x1 squared. And if we look at the result of that with the do, then what it's done is it's built us a new data frame with all the information that we need from the tidy, together with the information that enables us to associate the particular group that was being used and the particular variable. So under x2 being 1, the first group, then there are 3 terms that were fitted, the intercept, the beta 1 and the beta 2, and these were the tidy columns, which was estimate, standard error, p-value and t-statistic and so forth. Okay, and similarly for group 2. So in that one call, we've fitted both models, we've tidied it all up, we've got a data frame that's got all the information we can possibly want to use there. Okay, and then let's build on.
Can I
Yep.
interrupt? Do you know how the authors, do this behind the scenes? Is it like some kind of like parallel processing, or because we could have this done like in a for loop, right? If you run it and do a second time and then roll by it into the same, that would give the same results, right? But do you have any idea how this is done? How fast this would be like if I run 100 regressions?
Okay.
Yeah.
So the question was the implementation details of the do, and the story behind the do is it's replacing things that we could do by other more low-level primitive operations. You could do a for loop and separate out this data, save it into a temporary variable, and then call the appropriate linear model for just that subset. What this does is it takes away all the it's this one. All the details of that have been swept under the carpet, and we've got a very sort of expressive way of doing that. The way it's implemented, I'm not sure. It may be as crude as just a for loop, and then we're back where we were before. I think increasingly what's happening is that these packages are becoming more and more blended into the environment in which they operate, so they will have features. I'm not sure whether this does, but it will do soon. If it doesn't, it will have features that exploit the multi-core environment, so that the for loop, if possible, is done in parallel, and so on. You can extend it in various ways. The answer is this any slower than doing it in a for loop? No, I don't think so. This is the preferred way to do it. It's much simpler to express it, and it won't take any longer. Yeah. And I think that's generally true in R these days. The programming facilities make it much smoother to implement things than previously have rather slow interpreted loops. Now it's much easier to move out to C if you want to, with the various packages that support that and all sorts of things. Another one of the very nice packages in the tidyverse is another one called Pure R, which is a package which adds a very kind of pure functional programming idioms to R, and that's discussed at quite a lot of length in the R for Data Science book, which I mentioned earlier, and I'm pretty sure that this will be implemented through that functional programming paradigm, which is going to be very cleanly implemented. Yeah. Okay, so that's talked about the parameter estimates. We can similarly get hold of the fitted values and the residuals and so on by doing, instead of a tidy, we could do an augment, and the result of that would be as shown here. So we get all our variables, and we get the fitted values and the residuals and so forth. So let's illustrate that in a plot. So in this plot here, first of all we draw the data as we've done before, which is the dots, and then we add another geometric layer, which is now going to be a line. This line is going to be dashed, it's going to have a line type dashed, and the data for which this line is constructed is not the original data, the DF data frame, it's the data frame fits that we've just built as the result of this augment operation. Come off the screen now. So this was saved into fits there. So fits is the data for this line layer, and this line is going to have x1 as the horizontal aesthetic for the dashed line, And the y-aesthetic, the vertical axis, is going to be the fitted values. So the fitted values were fitted under that quadratic model, and so we'll get a red dashed line corresponding to x2 is 1, and another blue line corresponding to where x2 is 2. So these are the two separate quadratic models that were fitted, and the lines are constructed via the fitted values. Okay. So if I just look again at the parameter estimates, so if I do a tidy rather than an augment, then these are the parameter estimates. And maybe I can just finish here, so I think we'll not have a lot of time to discuss this, but if you've seen the idea of a bootstrap, have people seen bootstrapping? Okay, so there is a way to do bootstrapping very nicely with these pipelines. So what I've done here is the following. So in contrast to these estimates here of standard errors, which involved the assumptions of normal errors and equal variances, in the bootstrap, you can, instead of constructing standard errors that way, what you can do is just replicate the data set by doing a random sample with replacement. If we do that many times, we'll get many replicates of the estimated parameter, and then we can look at the distribution of that, and that will give us a way of constructing standard errors. So the way in which you can build that into your DPLR pipelines is using this bootstrap command. And the bootstrap command takes the data on the left-hand side, which is our data frame just where x2 is 1. So unlike in the group by operation earlier, I've split it out into two separate calculations. So here x2 equals 1. When you do a bootstrap 1000, it will take the data on the left-hand side and it will produce 1000 replicates, sampling with replacement, of that data frame. And then we pipe that through a tidy linear model, quadratic linear model. And if we group by the different terms, so the term is whether it's intercept an x1 variable or an x1 squared variable, and then the summary of this group by version of the output of all that is, let's call it estimate and SE. So the estimate is going to be the mean of those estimates. So remember, we're going to get one of these per bootstrap replicate. There are 1000 of them, so we're going to get a mean of 1000 quantities, which is returned in EST. And if those 1000 estimates, if we take their standard deviation as an estimate, a bootstrap estimate for the standard error. So doing that, we obtain these quantities here, which if we compare them, so this is saying the, let's take x1. So x1, the estimate from the bootstrap is minus 0.39. Here it's minus 0.43, and the standard error is 0.568, and this has a standard error of 0.461. So notice there's some discrepancy there. Remember, this is using normal assumptions for the residuals. This is not. This is using bootstrap resampling methods. So we can sort of contrast those. Yep.
Is there any rule of thumb in selecting the sample for the bootstrap? Like 1000 here? How many? What is?
Do you say rule of thumb?
Yeah.
Yeah. Okay. So 1000 is plenty, I can assure you. You could do. It doesn't take very long, as we saw. You could do 100 to get it started to get some idea.
How many rows do we have in the original sample? I couldn't recall.
100.
How many?
100 rows, 100 observations.
No. I mean the original where we draw this bootstrap sample. How many?
1000.
How large is the size?
1000. So there are 1000 replicates of this data frame. So it's big.
No. I mean you draw. Oh, okay.
So the 1000
So
independent samples drawn with replacement,
okay.
which will give you 1000 estimated parameters. So lots of models are being fitted at this time.
Okay. But the size of each bootstrap sample, I got confused here. So when you do a bootstrap, it is not like a subsample of the original sample. It's just
This is 1000 samples sampling with replacement from the original one. So there'll be of size, what would be 50, I guess. Since x2 is 1, so there'll be half of them. And I do that 1000 times. fit 1,000 models, get 1,000 estimates, take their mean estimate. Yeah. So there's a lot of for loops in there that have been washed away in this little simple paradigm as shown here. Okay. I need to sort of be conscious of time to finish reasonably on time. So in the next bit, we do it for x2 is 2 rather than x2 is 1. I think that's all for that. Okay, so let's just summarise what we're doing quickly with this. So with an R markdown file, you can have text, you can have R chunks and their output, which can be textual or graphical, and it all gets inserted in together. If you take that document, then the verb is to knit it. So if you knit to PDF, then it runs R on all the chunks. It runs, so to get to PDF you go via LaTeX. So there's a converter from R Markdown to LaTeX, and then it runs LaTeX on the result, and sure enough, unfortunately it's got that, let's make it a bit wider maybe. Okay, there we are. So this is my PDF, which is in a PDF viewer supplied by RStudio, but you could save the file as a PDF file. And this is all the stuff. So it's got the graphics, the R output, and the rather meagre amounts of explanatory text that I've included in here into our document. So that's a PDF document. So that's one way to build these documents, and I just quickly finish by showing you some other ways. So this is where I included a file I'd already edited and created, the R Markdown. You can sort of start from scratch by so new file. If you say R Notebook, it will give you this little template here, and the output here is HTML Notebook rather than PDF Notebook. And what you get is so this little template you can edit. So it gives you just a modest example. You can delete and modify this to your own needs. It will have the graphics in and the R output in. The code is executed in the console window, which you can bring up to here. So this is a way of building an R notebook, and this renders to an HTML file, as it says. But alternatively, if you change that output to a PDF document, then it will render to PDF rather than to HTML. So you can go either way. You can build notebooks for web viewing of HTML form or PDF form, as I've shown. So this idea of having all the graphics, the code and the text all bundled into the same file, I think it is a great step forward from editing lots of different versions of your information and then sort of bringing them together by hand. Perhaps I could pick up on the earlier question just about how things are implemented here. So I think, I don't know specifically how the do command is implemented, but it's open source. We could check that very easily. I think I would suspect it was implemented reasonably efficiently. Certainly wouldn't be slower than writing the very clumsy for loops and doing it all independently. And I think what's happening now is that these tools are both much more expressive and much easier to use, and also much more powerful. They work with really quite big data sets, gigabytes of data, thousands, millions of rows, no problem on single core machines. But what's happening now, and I think it's very exciting to understand these exploratory data wrangling tasks and understand how they can actually get migrated into even bigger data sets. So what's happening now is that instead of the emphasis being on a multi-core or even single core machine with data local, then maybe your data is sufficiently large that it has to be spread across many sites, and you get a kind of cluster computer version of this. And then you've got to think very carefully about whether your algorithms, how they will parallelize across data assembled like that. So the data may be partitioned into maybe a Hadoop style distributed data set across multiple machines, and can you still do DPLR type data wrangling with data of that scale? Now the tools and techniques for doing that are starting to emerge. On these platforms, often you might go the Spark route. So Spark gives you a Scala or Python language framework for doing distributed calculations in this environment. The question is, can we bring all that to bear with our R tools as well?